In this lesson, we're going to take a look at the rotational kinematics model, which deals with objects that rotate. The format is very similar to the kinematics model that deals with linear motion. This just deals with things like rotating tires, axles, or anything that can spin. So I'm going to draw a picture of an axle here in a car. And we're going to say that this axle is initially not rotating. So we're going to say that it has initial angular velocity of 0 radians per second. This is the Greek letter omega right here that we use to denote angular velocity as opposed to linear velocity. And omega. And we're going to say that in 3 seconds, in time of 3 seconds, we're going to accelerate this thing to an angular velocity of 45 revolutions per minute. Notice how the units are a little bit different. I want to show you this example so you can see what type of conversions we might have to do. So in the given, I'm going to do the conversion so that I'm in the correct consistent units from the get-go. So we want radians per second, so 1 minute is equal to 60 seconds. And 1 revolution is 2 pi radians. So my minutes cancel there, my revolutions cancel there, and I'm left with radians per second. And when you do the calculation here, this is 4.71 radians per second. So initial and final velocities and time. And what I'm going to solve for here is the angular acceleration. Previously we used the letter A. Now we're going to use the Greek symbol alpha for angular acceleration. And we want to find out through how many rotations it goes through, theta. So in general, just to kind of take a look here, in the linear model we dealt with displacements, velocities, and accelerations. In the rotational world, they are thetas, omegas, and alphas. It follows the same procedures we did with the kinematics model in the first semester. So the equations are, and you'll see the similarities here in a second, theta is equal to theta 0 plus omega 0 t plus 1/2 alpha t squared. Omega is equal to omega 0 plus alpha t, and omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. And again, for the kinematics model to hold, the acceleration must be a constant. We have constant angular acceleration, which is the same condition for the linear kinematics model. Step 2, we list the variables. Theta 0, theta, omega 0, omega, and do it in the same order every time so we can get a good look at the variables here, and so we do it orderly every time. Now, in linear kinematics, we put the ruler on the ground for, let's say, a car that was traveling, and we said that that's 0. Well, here what we're going to do is we're going to put a protractor, if you will, a protractor, and we're going to say that's 0, and then we're going to measure revolutions from that. So wherever we say we're going to measure from, we count that as 0, and how far it rotates, or through what angle it rotates, is the theta. This is, I guess, be theta 0 here and theta, and we don't know that. The omega 0 we do know it's at rest, 0 radians per second, and we want to get to 4.71 radians per second, which we calculated in the given there, and we do not know the angular acceleration, alpha, but we do know this takes 3 seconds of time. So we list the equations, we list the variables, and then we go to the solve part. Step 3, solve. So to find the angular acceleration, looks like we're going to use the second equation here. So alpha is equal to omega minus omega 0 over t, which is 4.71 divided by 3, is minus 0, which is 1.57 radians per second squared, very similar to meters per second squared, which means I gain 1.57 radians per second every 1 second. And we want to know through how many rotations this goes through. So it looks like the first equation. One half alpha t squared. We start off at 0 here. The initial velocity is 0. So we're basically left with 1 half 1.57 times the time squared. And this comes out to be 7.06 radians. And roughly, this is, if you want to speak of revolutions, this is the final answer. But in terms of revolutions, we can maybe get a little better handle on this. 7.06 radians, if you do the 2 pi conversion, is about 1.12 revolutions. So in a 3-second time frame, it'll go 1.1 revolutions, and it'll go from 0 to 4.71 radians per second. So we can apply the kinematics model directly to this. So it's the same procedure as we did before. We list the equations, we list the variables, and we solve. And if you look at the equations here, they're very similar to the linear kinematic model equations. And those are the 3 steps you follow for a rotational kinematics model problem.